is this week. Okay, two of them are this week. One next week, which is on Wednesday, and the other one in 2 weeks, which is your date for the final exam. So we're almost done with the session. Okay, so just to remind you, today you're going to have two quizzes in your lab. You're going to do experiment 10 and experiment 11. Okay, so we're going to start now with chapter 10. And if you're going to look at this, as I've told you last time, this is just a continuation of chapter 9. When I say this is just a continuation of chapter 9, we're still going to deal here with the Lewis structure. Okay? So if we're going to look at the molecular geometry and the chemical bonding theory, okay? So this chapter is more on how, okay, the Lewis structure predicted the molecular theory. Okay? So what will happen in the first part of the chapter, we're going to do how that we're able to predict the molecular geometry based on the Lewis structure. And the last part of the chapter is we're going to look at the different theories that dictates the behavior of the atoms, okay, or of the subatomic particles within the atoms, or how atoms bonded with one another. Okay, because right now Lewis structure is one chemical bonding theories, but there are other we could say bonding theories that we have, and this is the most important chapter if you're going to take your organic chemistry. Okay, now molecular geometry, if we're going to look at this is the general shape of a molecule as determined by the relative positions of the atomic nuclei. So if you're going to look at the molecular theory, that's the three-dimensional arrangement of atoms in a molecule. Okay, so if we're going to do it, so 3D arrangement of atoms in a molecule. Now, geometry is very important because it's going to affect the what we call physical and chemical properties such as boiling point, melting point, and the types of reaction it undergoes. Okay. Now, what dictated this so-called molecular geometry? So the one that dictated this molecular geometry is the so-called BESFER, the valence shell electron pair repulsion model. It predicts the shapes of molecules and ions by assuming that the valence shell electron pairs are arranged about each atom so that the electron pair are kept as far away from another pair as possible. Okay, so why do you have to arrange it in such a way? Because you know electrons are made up of what? Negative charge. So if there's a negative charge and another negative charge, they will repel. Okay, so the BESFER predicts the shapes of the molecules and ions by assuming, okay, that the electrons pair are arranged in such a way the atoms about each atom so that the electron pairs are kept as far away as possible from one another, thereby minimizing electron pair repulsion. So we could say the BESFER accounts for the geometric arrangement of the electron pairs around a central atom in terms of the electrostatic repulsion between the electron pair. So in that case, you have to open your imagination because you have to think three-dimensional in this case. Now, although I will give you some sort of a guide during your exam so that you don't need to memorize them, you still need to know how to use that guide. Okay, so just like the so-called what we call periodic table, you're going to be given a guide. I'm trying to open up here so you will have an idea what it is. Okay, so I'm going to give it to you. I'm trying to find where it is. So this is the guide that will be given to you. I try to share so you will have an idea what it is. So share. So here. So this is the guide that will be given to you. Okay. So you should be able to know, okay, what does this mean? Because if you're just going to look at this out, you will tell you, oh, what is that? What does it mean? Okay, so as you could going to see here, it shows you some sort of term, okay, telling you the number of electron regions, the electron geometry, the number of bonding regions, the number of non-bonding regions, and the corresponding molecular orbital, and even the hybrid orbitals, and some examples are given here. Okay, so you don't have to worry in memorizing them. As I have told you, this is not a course on memorization, so you don't need to do memorization. So in such a way, when we're talking about predicting the molecular geometry, we're doing it in such a way that we don't put the electron pairs close to one another. So if you have, let's say, a central atom and two bonding pairs, the only arrangement wherein the electron pairs will be far away from another is in this way, wherein you have 180 degree Celsius, 180 degree angle, and the shape or geometry that you form is what we call linear. Okay. Now, if you have what we call three electron pairs connected to a central atom, so the bond angle that you have, there's 120 degree uh, angle. Okay, and if this is 4, you're not going to arrange it like a cross like this one. Why? Because we are in a three-dimensional. So the best arrangement that you have, if you're going to line it up, it's like this one. So you have there a bond angle of around 109.5 angle. So for three electron pairs, okay, you have a trigonal planar. For four, what we call electron pairs, that's what we call tetrahedral. So each of the electron pairs that we have here are bonding. Because later on, when the bonding becomes non-bonding, then that will be chains. There will be different shape. Okay? So I would suggest, since it's not mentioned here, I don't know if it shows here any bond angle. So that's the thing that you need to know. But if you're going to look at the figures that you have here, so you could right away predict that, oh, this is 180, this is 120, and this is 109.5. So as you could see here now, so you see here, so these are three bonding pairs, and then what happened if one of the bonding pairs become a lone pairs? So you have another shape, and we're going to go on that as we go on. Okay. Now, if we're going to have 5 bonding pairs, so the shape that you have there is a trigonal bipyramidal. So you could say two pyramids upside down. Okay. And the bond angle that you have there is either between 90 degrees Celsius and 120 degrees Celsius. So if you're going to look at this, another way to do it is like that. Okay. So the 90 degrees is the one here, and the 120 degrees, it's just like you have a Y, and then there's a line that you have here. That's why if you're going to look at it, that's a trigonal bipyramidal. Okay. Now, if you have 6 bonding pairs, you have the shape that is called octahedral, and all of the bond angle is around 90 degree angle. And if we're going to look at it in terms of another way, like a balloon, so this is how it looks like. Unfortunately, I don't have the model. I think in my other recording, you could see that I have a model there. Okay. I'm supposed to go to the office today, but unfortunately, some emergency happened at home, so I wasn't able to go. Okay. So if we're going to change now, some of the electron pairs from bonding pairs to non-bonding pairs or lone pairs, there's a corresponding shape for that. So as I've shown you in your what we call table here that will be made available to you, this the same file will be available for you in your exam, your not exam, your chapter quiz and also your final exam. Okay, so if one of the bonding pairs become a lone pair, so as you could see here, two bonding pairs, one lone pair, but there's still three electron pair region. So one of the bonding pairs there becomes a lone pair. And the shape that you have there is now what we call bent. Now, if you have a tetrahedral and one of the bonding pairs becomes a lone pair, you have now the shape of the trigonal pyramidal. And if there's two uh, lone pairs and two bonding pairs, we have the so-called bent. Okay? And if you're going to look at the one that has five bonding pairs and what happens, one of them becomes a lone pairs, you have a seesaw. So if you're going to look at the seesaw shape here, so remember, you have, try to look at this one here. So if you have, let's say like this, right? And this one becomes a non-bonding pair. So that's the seesaw looks like. Okay, so we have a dot there that denotes the lone pairs. Now, if two of them has what we call the lone pairs, so you have there a T. Okay, like Mr. T. I don't know if you know that actor with the name of Mr. T. Okay, and if three of them is a lone, three of them becomes a lone pairs, so you have the linear. And if you have an octahedral, so if one of them becomes what we call a lone pair, so this is how you look at it, square pyramidal. And then if two of them becomes a lone pair, so usually they're on opposite side, so you have a square planar. Okay. Now what you're going to do is you're going to be given an atom, and you're going to predict what's the shape of the given not atom, molecule. So how are we going to do that? So knowledge of your Lewis structure still needed here. So the only difference here, if you have a best pair model, if ever you have multiple bonds, like a double bond or a triple bond, okay, you will treat it as one bonding pair, one electron pair. When you have electron resonance structures required in the electron dot symbol, you may choose any one to determine the electron pair arrangement and the corresponding molecular geometry. So how are we going to do this determination of molecular geometry or shape using the best pair? So if you're going to look at this, the first thing that you're going to do is what you have done in the Lewis structure. You determine the Lewis structure or the electron dot formula from the given chemical formula. And then based on the what we call electron dot formula, you determine the number of electron pairs around the central atom, including the bonding and non-bonding pairs. And then after that, you determine the arrangement of the electron pairs about the central atom, just like the different figures that we have. And then you obtain the molecular geometry from the directions of the bonding pairs for this arrangement. Okay, so this is just a continuation of your what we call Lewis structure. Okay, so the example that I have here are given here. So I like to change the example that we have here so that you can have what we call more examples, because if you're going to look at the previous recordings that I have, I already have some examples that were given, and mostly most of these examples are the one, okay, that you seen here. So instead of ASF3, what if I'm going to use, let's say, IF4 plus? So there's already an answer for this one in my other recording. I just want to expand the example that I have. So you will be able to have more example when you review it before the quiz. Okay. Maybe the other one, I can use a PF3. So I just replace it with familiar or almost similar molecule that I have here. So maybe I put here that this is the PF3 and this is the pH, the what we call IF4 plus. Okay. So if this is the PF3, what's the first thing that we're going to do? We determine the, okay, valence electrons. So you have there 5 plus 3 times 7. Okay. So you have here what? 21 plus 5. So that's 26. And then what we're going to do, we're going to use 6 of them as your connecting the bond or your bonding pair. Okay. So you still have 20 and then you use 6 in each of the fluorine. So you use 18. So you still have 2. You have this. So what's the shape of PF3? Okay. So if you're going to look at this, how are you going to determine the shape of your PF3 here? So what you're going to do, you look at the bonding pairs that you have here. So you have 3 bonding pairs. And then you have here 1 lone pair. So that means overall you have 4 electron pairs. So you can also arrange it in such a way that it will give you the shape. What shape is that? Okay, so that is your trigonal pyramidal. So that's the type of questions that you can expect in your chapter quizzes and maybe in your exam. Okay, so this is the trigonal pyramidal, and the way that you're going to determine it is just using the Lewis structure. Now, how about IF4 plus? So what are we going to do? The same thing. The valence electron, and then 4 times 7. And then what is this? Plus or minus? If we have a positive charge. So since we have a positive charge, that's a minus. Okay. So this is 28 plus 7. That's 35 plus 1. You have 36. And then you're going to use how many? 8? So minus 8. So you still have 28. Okay. And then you're going to use 6 for each fluorine. So 6 times 4 will give you what? 24. So you still have 4. So you have here this one. Am I right here? What do you think? Did I miss something? I7 is 28 plus 7, 35, right? Oh, is it minus? So this should be 34. There. Because something is missing. That's why I said, am I right here? Instead of adding what we called me adding the thing, it should be subtracted because 35 minus 4, so that's 34. So this becomes 26. So this is 2. So you only have one lone pair there. So what we're going to do is we're going to find something that has 4 bonding pairs and 1 lone pair, or the one that has 5 electron pairs. So you started with the 5 electron pairs, and then you're going to find what's the shape that has this one. So if you're going to arrange it in such a way, I think this is how it's going to look like. So you put a bracket because it has a charge. So this is what? A seesaw shape. Okay? Now the last but not the least here is the CLF3. So you have what? 7 plus 3 times 7. So you have here a 21 plus 7. So you have 28. And then what you're going to do, you connect them. So you use 6 electrons as bonding pairs. So you still have 22. And then you're going to use 6 for each of the fluorines. So 6 times 3, you have 18. So 22 minus 18, that's 4. So you have it like that. And you have 3 bonding pairs plus 2 lone pairs. So you will have here a T shape. So ask yourself, can you solve problems like this? And as I've told you, you can look at the answers of the molecules that's given here in the original slide. There's another recording that we have there from the previous fall semester. Analyze. Don't be shy. If you have question, this is the time that you can ask that question. And if I'm not mistaken, there's still another questions that we have here using IC, asking you what's the molecular shape. If you have an ICL3, I think it's just the same as your CLF3. That is, it's going to give you a T shape. And then an ICL4 minus, so maybe, although I already recorded that one, maybe I can replace it with another one. So maybe a BRF4 minus. So this is similar to the previous one that we have, the CLF3. So that means it's a T shape. Now, if we're going to replace it with this one, but they have the same number. So you have what? 7 plus 4 times 7 plus 1. So that will give you 36. And if you're going to do this thing, maybe you will have it like that one. So the 36, you use 8. So you have 28. And then 6 in each of the fluorine. So 6 times 4. So that's 24. So you still have 4. So you have that one. So you will have an AX4E2. So this is how you symbolize this thing. The central atom, the X is the bonding pair, and the E is the lone pair. So if you're going to put it here, so this is an AX3E. Okay? 3 bonding pairs, 1 lone pairs. And this one is an AX4E. 4 bonding pairs and 1 lone pairs. While this one is an AX3 E2. Now you can see it in your, here, see this one here. So that's what it means. So instead of X here, they put B. Okay, B for the bonding pairs. So I hope you're not going to be confused on that thing. So I think you don't see the one. So this is what I mean there. So instead of an AX, they use here an AB. B is for bonding pairs. Okay. Now, as I have told you, you need to know the bond angles that you have. Oh, before we do it, this is what? A square planar. So how you be guided here if you have what we call this table here. So you go to the one that has an AB4E2. So that's the one here. So that means you have 4 bonding pairs and 2 lone pairs. So the corresponding shape of that or geometry is a square planar. Okay. Now, how about predicting the bond angle? So we already mentioned the bond angles for each of the geometry that we have. So we can have the bond angles 180 degree, 120 degrees, and 109.5 degrees, and so on. Okay. But usually, these bond angles deviate. They can be bigger or lower, higher or lower than this one, depending on the conditions of a given molecule. So if we have a lone pair, okay, so the lone pair requires more space compared to the bonding pairs. So if it requires more space, so that means it will exhibit some uh, changes. Will give some changes to the bond angle. Remember, what's the difference with the lone pair? So when you have a lone pair, it is occupied only by one atom, compared to what we call the bonding pair, where it is occupied or shared by at least 2 atoms. So if you have a lone pair, usually it's just alone on a given atom. So they have more space compared to the one that has what we call bonding pair. Okay, so usually in most of this discussion, we have it like this, like a head of an alien. So this one just denote that you have a lone pair. Okay, bonding pair usually denote by a line. One line is made up of 2 electrons. Okay, so what happened? So if we're going to look at the not trigonal, tetrahedral shape of molecule, originally, if you have the same atoms attached to a central atom, the bond angle is 109.5. But if one of them is replaced by another atom, there is a corresponding effect on the bond angle. So for instance, you replace chlorine in one of the hydrogen. Chlorine is more electronegative, okay, compared to the hydrogen. So what happened? So the chlorine will abstract or at least pull the electron towards itself. So from 109.5, there's an increase in the bond angle, okay, with respect to carbon-hydrogen bond angle, because the chlorine was pulled out pulled the electron towards itself. But if these electron pairs becomes a lone pairs, okay, the space that you have here will force the bond angle here to become what? Smaller. So the electron repulsions that you have here will force the bond angle there to be smaller. So from the original 109.5, it becomes 107. And if you're going to replace another bonding pair into a lone pair, it will make the bond angle of the carbon to hydrogen much less, or oxygen to hydrogen here, because of the electron pair repulsion that it exhibits. So you have more lone pairs there. There's more space for the electron. Okay. And electron and electron, they will repel one another. Okay, now what happened on the other hand if you have multiple bonds? So what's the difference of multiple bond compared to a single bond? So a multiple bond, you have to have more electrons. And since you have more electrons, there's a tendency for repulsion. So from the original what? 120, if you have three bonding pairs, if you're going to replace one of them with a bond angle, like oxygen here instead of hydrogen, so from 120, this one will repel, okay, this thing producing 116. Now, if you're going to ask me what would be the bond angle here, so most likely it's more than 120. Okay. Now, if instead of what we call oxygen that you have here, you have another, we could say carbon. So the effect is a little bit smaller because what's the difference between these two? Remember, you have these lone pairs here for your oxygen. So that additional lone pairs that you have here will repel, okay, making the bond angle of carbon and oxygen with respect to hydrogen more than 120, but the one that you have here is less than 120. So the same thing as here. So this is less because you have a bonding pair here instead of a lone pair that you have observed here in your oxygen. Okay? Now, one thing that you need to know, aside from determining the molecular geometry, is the so-called dipole moment. Now, you were introduced already, if I'm not mistaken, in chapter 8, the concept of a polar bond. Now, when you have a polar bond, you're only what? Comparing two atoms. And you are asked if they form a bond, if that bond is polar. So for instance, if you have, let's say, F and F, we could say that the bond is nonpolar. Why? Their electronegativity difference is just equals to 0. But if you are asked between hydrogen and fluorine, if you are asked if the bond is polar, you could say it's polar. Why? Because there's a tendency that the electron will go towards the fluorine because it's the more electronegativity difference. Okay, it will pull the electrons toward itself. Now, how is the dipole moment similar or different with this concept that we have learned in chapter 8? Okay, so when we're talking about the dipole moment, this is just the quantitative measure of the degree of charge separation in a molecule. Okay, now dipole moment, you can get the dipole moment if you have a molecule like this one, the so-called uh, binary compound that's made up of two atoms. So if you're going to ask the dipole moment for this F, you could say it's equals to 0. Why? Because they're symmetrical. But if you're going to determine the dipole moment for HF, you could say that it's not equals to 0. Why? Because there is an overall degree of charge separation. Okay? So how do we do these measurements in the dipole moment? So you do this measurement based on the fact that polar molecules are oriented by an electric field. Why are they oriented towards an electric field? Because this will become a partially negative charge and this will become a partially positive charge. You cannot see a partially negative and a partially positive charge in a non-polar atoms. Okay? So once you see a partially negative and a partially positive charge, you can orient them in the electron field. How? So if there's no electric field, there's a random arrangement or orientation of the molecules. But if you put an electric field, you will see the partially negative will go towards the positive charge. The partially positive will go to the negative charge. Okay? And as I have told you, we discussed about the polar bond. This is just characterized by the electrical charge. So polar molecules has non-zero dipole moments. So for HCl, just like the HF that we have discussed earlier, we can have the degree of separations like this. Why is this negative? Because this is the more electronegative atom compared to this one. Okay? So if you're going to look at them in terms of the orbitals that you have discussed, that we have discussed in chapter 7, okay? So this is how it looks like. Now, what happened if we have more than, let's say, one bonding pairs? Because it's easy if it's just one bonding pairs. All you need to know is look at the direction or which one is the more electronegative. But what if we have more than one? If we have more than one, what we do is we're going to look at the vectors and then we sum them. If the sum of the vector is zero, then the dipole moment is zero, and we could say it is nonpolar. But if there is a net vector, then the molecule is polar, or the dipole moment is non-zero. Then this best exemplified why we have different properties if we compare CO2 versus water. They're the same in such a way that you have what? One central atom connected by two atoms of the same kind. But why do they have different properties? In fact, they even have different molecular shape. Okay? So the best way to do that is look at the vectors. So between carbon and oxygen, you have here what? Oxygen more electronegative than carbon, so you have this thing. So this is a partially negative, this is the partially negative. But what you could see at the vectors, they are opposite one another. So if you're going to sum them up, your dipole moment is zero. And if it's zero, you could say this is non-polar. Okay? But if you're going to look at water, which is the same, we could say one central atom connected with two other atoms. So between oxygen and hydrogen, oxygen is more electronegative, and the arrangement that they have here, so this is what? Linear, and this is bent. So if you're going to look at it, it's going towards the oxygen. And if it's going towards the oxygen, there is a vector that is not zero at the end. So it's towards the oxygen. So you can see this is your partially positive end. Oh, not partially positive. That's your partially negative end. And this is your partially positive end. And this is your partially positive end. So there's a net vector there. And since there's a net vector there, so if we could say the dipole moment here is equals to zero, here, the dipole moment is not equals to zero. So this one is non-polar, and this one is polar. Now, you can predict whether you have a polar or a non-polar atom by just looking at the formula. Remember the AXE that we have mentioned earlier? So we could say this is an AX 2E, then this is an AX3E, an AX 3E2, this is an AX4E, and this is an AX4E2, and this is an AX5E. Okay? So if you have, let's say, an AXN, no lone pairs, and assuming all the X are the same, what do you see? Okay, except AX1. Okay? So if you have an AXN, n is equals or more than 2, all of them are what? Nonpolar. Assuming that the x are the same. But if you change one of the x, then it will become non-zero. Okay? The rest, if you have what we call lone pairs, like the one that you've seen here, it can be non-zero. You still have to check. But most probably it will be non-zero. The only difference is the square planar. Because if you're going to look at the square planar, this is how it's arranged. So all of them cancel out, giving you a net vector that is equals to 0. Okay? So polar molecules experience attractive forces between molecules. And in response, they orient themselves in a partially positive and a partially negative manner. And it has an impact on the molecular properties such as boiling point. And usually these attractive forces due to polarity lead to the molecule having a higher boiling point. Okay? Because the forces that they have, there's electrostatic in nature. Okay? So you can see this observation if you have these compounds. So what can you say about these compounds? They are made up of the same CH2, oh wait, C2H2Cl2. They have the same molar mass. But what's the difference? One is arranged wherein atoms of the same kind are on the same side, like this one. And this one, they are arranged opposite. So that's the cis, and this is what we call the trans. Okay? And that term has something to do with the event that we have yesterday, the Pride Day that we have, right? The cis trans thing. Okay? But if you're going to look at the boiling point that they have, how come this is much higher compared to this one? Well, it has something to do with the net dipole moment that you have. So here, since they are opposite, they will just has a dipole moment equals to 0. So this is a non-polar substances. But this one, chlorine being more electronegative than hydrogen, so the electrons will go towards the chlorine. So we could say this is the partially negative end, and this is the partially positive end. So another way to do, you see this one here, like the crosscut of Kylo Ren. Okay, if you have this one, so that means there's a partially positive end, and that one's partially negative end. And its effect can be observed in the boiling point. Okay, analyze. So let's try to predict this one. So here, what you're going to do is you're still doing the Lewis structure. You can predict the molecular shape, and in addition to that, you can ask whether this is a polar or non-polar. Okay, GF4. So maybe we could just do right away here. So germanium would have what, 4, and then 4 times 7. So you have here, if I'm not mistaken, 28. That's 32. So minus 8. So you will have here 24. So right away you have this. This is what? Tetrahedral. Now, is this polar or non-polar? Or we could say this one, okay, its dipole moment is equals to 0 because they just cancel out. So this is a non-polar substance. And then we have the SF2. So you have S, which I'm not mistaken, is 6 bonding pairs. And then you have what? 2 times 7. So that's 14. So you have here 20. So maybe you can do it like this. So 20 minus 4. So you have 16. And you have here what? 6 times 2, that's 12. So you still have, we could say 4 here. So this is a bent or V shape. So there's a lone pair. So you could say it's a non-zero dipole moment. So most likely it is a polar substances. Okay. Now XEF2. So how is it different from the SF2? So this one has 8. And then you 2 times 7. So you have here 22. So if you're going to look at here, minus 4. So you still have what? 18. And you use 12 here. So you just have 6 electrons as non-bonding pairs or lone pairs. Okay, so this is, we could say, linear. And based on this one, okay, you can just see it here. So what can you say? Since it's linear, it has a 0 dipole moment, so this is non-polar. Now you might say, how is this different from that one? This one would have a shape like this. Compared to this one, wherein you have here, you have here, and you have here as your what we call lone pairs. So this is non-polar. So I hope you see the difference between the two. And last but not the least, ASF3. So if I'm not mistaken, arsenic would have what? 5. So 3 times 7, 21, 26. So you have there 26 minus 6, that's 20. So you have here 3 times 6. So that's 18. So you have that one. Since you have a lone pair here, okay, even though everything goes towards the fluorine, you still have a net charge that is not equals to 0, a non-zero one. So this is what? Trigonal pyramidal. Since the dipole moment is not equals to 0, so you could say this is polar. So those are the questions that you can be asked. Instead of given 0 dipole moment, you will be asked is, which of the following is polar? Which of the following is non-polar? Okay? Now, let's go to this so-called chemical bond theory. Okay? So the valence bond theory, the BBT. So if you're going to look at the valence bond theory, it's an approximate theory put forth to explain the electron pair or covalent bond by quantum mechanics. So if you're going to look at the VVT, it gives a clearer picture of chemical bond formation from Lewis theory, okay, or then Lewis theory. So what we have so far, the Lewis theory, and then we use the Lewis structure in the BSPEPR to predict the molecular shape, and then from that we can predict what we call the polarity. Now, the valence band theory, it gives a clearer picture of the chemical bond formation than the Lewis theory. So what does the BBT said? It states that a stable molecule forms from reacting atoms when the potential of energy of the system has decreased to a minimum. So what does it mean? In BBT, a bond forms when an orbital of one atom comes to occupy a portion of the same region of space as an orbital of the other atom. And the two orbitals are said to overlap. And usually the total number of electrons in both orbitals is no more than 2. So it still maintains the definition that an orbital can accommodate at most 2 electrons. Okay? And they said the greater the overlap, the stronger is the bond. Now the orbitals bond, except for the s orbitals, okay, they bond in the direction in which they protrude or point so as to obtain the maximum overlap. Okay? So in the BBT theory, what we have here is the so-called of hybridization. Now, what is this hybridization? So when we're talking about hybridization, this is just mixing of two or more atomic orbitals to form a new set of hybrid orbitals. So hybrid orbitals are orbitals used to describe the bonding that is obtained by taking combinations of the atomic orbitals of the isolated atom. So what does this mean? Your S can mix with a P and a D orbital to give you, let's say, an sp orbital, an sp2 orbitals, and so on. Okay? And the number of hybrid orbitals formed always equals the number of atomic orbitals used. So what does this mean? When you have one s orbital mixing with one p orbital, you're going to get two sp orbital. When you have one s orbital mixing with two p orbitals, you're going to get three sp2. Okay, so you see this one, sp, one s and one p orbitals, sp2, one s and two p orbitals. If you mix one s and three p, you have an sp3 orbitals. If you're going to mix one s, three p, and one d, you have an sp3d orbitals. If you're going to mix one s, three p, and two d orbitals, you have six sp3d2 orbitals. How does the mixing happen? Or how does, okay, this mixing, we could say, takes place? Oops. So if we're going to look at how the mixing is happening, so maybe you still remember the S is usually lower than the P orbitals. So once they do hybridization, they're going to form a new orbital. So this is just, we could say, an sp3 orbital. Now, if it's just an sp2, we could say you still have the p there, and then what happened is the energy level is a little bit lower than the p orbital. Okay, so that's how the mixing coming to happen. Now, you can denote the hybrid orbitals to a specific geometric arrangement. Remember here in the molecular geometry, this is the hybridization that you have. See this? So the linear, you have sp, the one that has the 3 has an sp2, the one that has the 4 is an sp3, the one that has a 5 has an sp3d or dsp3, the one that has a 6 has an sp3d2. So you can have an additional question there. What is the hybridization? And usually it refers to the central atom. What is the hybridization of the central atom in BEF2, in BF3, in CH4, in PCl5, and SF6? So all you need to do is add what's the number that you have. So 1s, 1p, that's 2. 1 plus 1. 1 plus 2, that's 3. 1 plus 3 is 4. 1 plus 3 plus 1, that's 5. 1 plus 3 plus 2, that's 6. And it matches the number of orbitals that you have there. So what can you say? Can you assure me that this is a sure points or sure correct answer in your chapter quizzes or chapter quiz? Okay. Now, if you're going to look at some of these hybridization orbitals, this is how they look like. So this is how an sp hybrid orbitals would look like: an sp2, an sp3, an sp3d, and an sp3d2. Okay. So this is just the same as linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. And the way that you're going to do hybridization, I think it's the same. It's just a continuation of what we have done. You write the Lewis structure and then use the best pair to determine the arrangement. And then from the arrangement, you deduce the hybrid orbitals. And then you assign the valence electron to the hybrid orbitals one at a time, pairing only when necessary. And then you form bonds by overlapping singly occupied hybrid orbitals with singly occupied orbitals of another atom. Okay? So for instance, if we're going to have, let's say, CH4, so the way that we're going to do this is we look at the carbon here. So how do we write the electron configuration of carbon? So 1s2, 2s2, 2p2. Right? So what does it mean? If we can go, this is what? 1s, 2s, and then this one. Now, what if we mix the S and the P orbital? And in mixing it, what happens? So we eliminate the 1s here. So what happened is we mix. Okay? So this is what we call the promotion. So when we say promotion, we promote one of the atom of the electrons here. And then we hybrid. So what we have here now is like this one. So this is an sp3 hybrid orbitals. So how does the hydrogen look like? So the hydrogen who just have one electron in an orbital. So each of these will bond with each of them. So you have 4 hydrogens. So you're going to have the dehybridization. So if you're going to look at this, how does an sp3 looks like? It's this one. So that is your carbon, and each of this one you have a hydrogen atom. So from the sp3, each of them has half-filled orbitals. So the other orbitals will come from each hydrogen. So that's how your valence bond theory looks at it. So it gives a clearer picture in the bonding compared to this, what we call Lewis structure. So promotion means one of your electron goes to a higher orbital of a higher energy level. Hybridization is the mixing of the s and the 3p orbitals. Okay. So this one has something to do with BF3. So how does the bonding between the boron and the fluorine takes place? So if you're going to look at this, this is how the electron configuration of boron at the ground state. So what happened? You're going to promote one of them here. So you have here now two p orbitals that's half filled and one s orbitals that half filled. So from promotion, you're going to mix them, hybridize. So you see the hybridization, it has an energy level that's higher than the s orbital but lower than the p orbital. And since they are half filled, okay, each fluorine has what? One unpaired electrons, and you can pair it up to form your BF bonds. And from that, you'll be able to do BF3. Try to analyze it. Okay? Just have to talk to something for a while. So that's how promotion and then hybridization takes place. You should have an idea about this because this is the first chapter that is being discussed in organic chemistry. And sometimes if the student don't get it, they're going to be left behind. Okay? So that's the importance that you have here of knowing this so-called hybridization. Okay? And what makes carbon a unique atom. Okay? Because it can undergo several hybridization, not only formation of sp3, you can form an sp2 or an sp. Okay? Now, we can do the valence bond theory to describe the bonding of a nitrogen atom in N2F2. And we're going to do the same thing as we have done earlier. So what are we going to do with the N? So if you're going to look at the N, okay, it has what? So 1s, 2s, and then you have a 2p. So what can happen? What if we're going to mix the s and the p orbitals? Okay, so we're going to have here an sp3, and it look like this. Okay, so when it is an sp3 orbital, consider using one of them as being bound to another nitrogen. So what does it mean? Maybe this one goes to another nitrogen, leaving you two more orbitals with F. Because if you're going to look at this, this is going to be like that one. Now, you may ask yourself, where does this sp orbital come from? Okay, so as you're going to look at this, only three orbitals of the sp3 form some sort of bonding. The other one that you have here is already filled up. So that can be observed in the form of another bond that you have. Okay? So the NN bond that you're going to have there, we could say is the overlap of what? A half filled sp3 orbitals on each other. So the lone pair occupies one sp3 orbital. This one here. Okay? Now how about ClF2? How is the hybridization here? So Cl, that's already third period. Okay? So you can have a 3s, then you have a 3p, and you can introduce already the 3d here. But as you will know, the only one that's filled up here would be the 3p. So what happened? You can promote, okay, one of the electrons here to go to the 3d orbital. So in that case, okay, you're going to have, I'll just show you the 3p and the 3d. So in the 3p, one of them is half filled, and in the 3d, one of them is also half filled. And what you're going to do is maybe hybridize them. So I really need to put the S. So when I hybridize this one, what will happen? I have one S, I have 3p, and I have 1d. And if I'm going to look at this, this is how it looks like. So how many half-filled orbitals do I have? Okay, I have here 2. Now, what does this represent? This represents as my, we could say, lone pairs. Because if I'm going to write the Lewis structure just as a comparison, ClF2. So what do I have here? I have 7. I have 2 times 7 plus 1. So I have here 14 plus 7, 21. I have 22. So if I have 22, I use 4. So I still have how many? 18. And then I use how many here? 12. So I still have 6. So this thing that we have here, if it's not a multiple bond or a bond in a multiple bond, it serves as your lone pairs. Or no, I would say this field orbitals, that's your lone pairs. Okay. The mistakes that I have here is I forgot that it's not a double bond. It's like this. So this is wrong. My mistake. So the one that I have here is filled up. That's a lone pair that you can see in your nitrogen. It's not a multiple bond. That's my mistake there. Okay? So this is what valence bond theory is all about. It gives really a clear picture compared to the Lewis structure. Okay? So you promote one of the electron to the next orbital of higher energy level, and then you mix the orbitals or you do hybridization. So usually one hybrid orbital is required for each bond, whether you have a single or a multiple bond, and then for each lone pair. Now, multiple bonding involves the overlap of one hybrid orbital and one for a double bond or 2 for a triple bond non-hybridized p orbital. So if you have a multiple bond, what is involved is a non-hybridized. Okay? And in each of these so-called multiple bond, there are 2 kinds of bonds. You have the sigma bond and the pi bond. So a sigma bond, it has a cylindrical shape about the bond axis. It is formed either when 2 s orbitals overlap or with directional orbitals, which is p or hybrid orbitals when they overlap along their x-axis. The pi bond, it is an electron distribution above and below the bond axis. and it's formed, okay, by the sideways overlap of two parallel p orbital. Okay, so when you have a sigma bond, usually you have one of them in each of these, we could say, bond. So when you have a single bond, you have one sigma bond. When you have a double bond, you have one sigma bond and one pi bond. If you have a triple bond, you have one sigma bond and two pi bond. Okay, so how this pi bond form and the sigma bond form? So if you have a sigma bond, usually it's formed by the overlap of your s orbitals, like that one. That's a sigma bond. Okay, now if it's a sigma bond between the p orbitals, this is how it looks like, how they overlap. Okay, now when there are two p orbitals that overlap sideways, you form there a pi bond. Okay, so if you're going to show the illustration on how the sigma and the pi bond form, so this is, we could say, the sigma, and if you're going to look sideways, that's your pi bond. Now if you have to see how is it when you have two pi bonds, so there's usually two sideways formation. And if you're going to look at this, when does the pi bond form? Usually it forms when you have a p orbitals that's not hybridized. If there are two p orbitals that's not hybridized, then you have a triple bond. Okay, so try to look at this. This is what, if you're going to look at the hybridization here, that's an sp2. So what does it mean? You have an extra p that's not used up. You have an extra p that's not hybridized. So that extra p, that would result to a pi bond. Now if you have an sp, how many p orbitals that's not used up? You have two. So in that case, you can have two pi bonds. So that's what happened if you have a triple bond. Just like what happened here in C2H2, which, if you're going to get the Lewis structure, would look like this. Are we clear on that? Do you think you can get it? If you're asked how many pi bond and how many sigma bond in this molecule. So those are the questions that you can expect. All you need to know, every bond, uh, single, double, or triple bond, it always have one sigma bond, and every double bond has one pi bond, and every triple bond has two pi bonds. Now, if you ask for the strength, the addition of a pi bond makes it a little bit stronger. But if you're going to what we could compare it, if you just have sigma versus the pi, I think the sigma is much stronger than the pi. But you usually cannot have the pi bond without the sigma bond. Okay? Because once you have the pi bond, that means you already have the sigma bond that is present there beforehand. Now, we can look at this pi bond to explain the cis-trans isomers that we have earlier. Okay? So in the cis-trans isomer, so as I mentioned earlier, why this one has a higher boiling point compared to this one, which in short, why is this stronger compared to this one? Okay. Now, what happened here? The overlap of the parallel pi orbitals restrict the rotation around the CC bond, and in this case, this fixes the geometric positions of the CL. So either it is on the same side or on different side. Okay? So in this case, when you're cis, you have more pi interaction compared to the CL-CR here. Okay? There's a restriction of the rotation of your C double bond, uh, C double bond thing. Okay? And that itself make them on the same side so they can have the phi orbitals or pi interaction between them. Now, you can also use this bonding to describe the carbon atom in a formaldehyde. Okay, so how are we going to describe this one? So you have here the presence of what? Two lone pairs and a multiple bond. So maybe what's the hybridization of your carbon here? So we can start by looking at, let's say, what do we have? 1s, 2s, 2p. And if you're going to look at the carbon, it's usually like this one, right? Now, when we promote them, what happened? Promotion would lead one of these electrons to go to the p orbital. So there's still a 2s and a 2p here. And then when you hybridize, do you think all the p orbitals will be mixed up? Okay. When you hybridize, what will happen? There's just an sp2 and one of your p will remain like that. So what happened here? Where does this bond formation came from? The CH sigma bond. So you have here what? There's a sigma bond here. Okay. It will form from the overlap of two. So I put here DH so you will know what it means. Okay. And then you also have a sigma bond here between a carbon and oxygen. And it's also being overlap of what? The sp2 hybrid orbitals. Okay. Now the question now that is being asked, how about this? What will happen to this? Okay. So what happened there is the formation of what we call the pi bond. And this one usually, okay, we could say if you have one of these p orbitals that's not hybridized, that results to one additional bond or one pi bond that gives you the double bond. I think, okay. So the way that we look at this BBT as atom approach one another, their atomic orbitals overlap and they form some sort of this molecular. No. Okay, that's another thing. So what we do here is 1, 2, 3 sigma bonds that came from sp2, and the additional bond that we have here that results to a double bond, that's the pi bond coming from an extra p orbitals that was not hybridized. Okay, so that is BBT. Now, in addition to BBT, there's another bonding theory that we're going to discuss. Okay, and in this bonding theory that we have, it comes up because they cannot explain what is happening to oxygen. the BBT or the valence band theory, you cannot satisfactorily account the properties of some molecules. Like for instance, this oxygen, it has no unpaired electron, but it is paramagnetic. What did we know from chapter 8? Okay, that if there's no unpaired electron, it should be diamagnetic, but experiment shows oxygen to be paramagnetic. Okay, so the BBT cannot account that. So whenever they cannot account something, they came up with a new theory, and that's where MOT came from. So when you have MOT, these are bonds that are formed from the interaction of atomic orbitals to form molecular orbitals. So as an atom approach one another, the atomic orbitals overlap and form the molecular orbitals. Okay, so if you're going to look at these molecular orbitals, they're concentrated in regions between the nuclei, and you call them the bonding molecular orbitals. Okay, they are what we call form or obtained by adding the atomic orbitals. So what happened if you mix atomic orbitals with one another, you form the molecular orbitals. Now the mixing would result in the bonding and anti-bonding molecular orbital. So one atomic orbital mixing with one atomic orbital, you form two molecular orbitals. Okay, one that is bonding and the one that is anti-bonding. So the energy level that they have, the bonding is lower compared to what we call the anti-bonding. And if you're going to look at this one, you can have a constructive interference that results to the bonding molecular orbital, or you can have the destructive interference that forms the anti-bonding orbital or molecular orbital. So a bonding molecular orbital, it has a lower energy and greater stability than the atomic orbitals from which it is formed. And an anti-bonding molecular orbital, it has a higher energy and lower stability than the atomic orbitals from which it was formed. Okay? So this is how the constructive and destructive interference happen. So you could see constructive is just addition, destructive is just, we could say, subtraction or cancellation of whatever stuff that you have there. Okay. Now, if you're going to look at these molecular orbitals, so we just look at the s orbital. What if we have the p orbitals? So remember, p orbitals, they have three orbitals within it, or three degenerate orbitals. So what you form is this one. And how are you going to fill it up? Well, depending on how many atoms you have in each orbital, you fill it up from the lowest to the highest energy level. Okay? And you can predict the bond order by just looking at this equation. So bond order is just equals to 1/2 of the number of electrons in bonding orbitals or bonding molecular orbitals minus the number of electrons in anti-bonding orbitals. Okay? We will have some example of this as we go on. So like this one. So if you have an H2 plus, so how many how many electrons do you have there? H2 plus, so there's a plus, so that means you only have one electron. Okay? And if you have one electron, you fill it up. So what you do? Okay? 1/2, so this is what? 1 minus 0 times 1/2, so you will have there 1/2. Okay? Now for H2, you have here 2 minus 0 gives you what? 2 times 1/2 of that. So you have there the bond order, and that corresponds to this. Now if you have He2 plus, so what is He2 plus? It's He would have what? We could say you want here, and the other one you have there. And when you fill them up, You have 2 here and then you have 1 there. So 2 minus 1 equals to 1 times 1 half will give you 1 half. Now, if you have it in terms of He2, so that means each He atom has 2 electrons on it, which you're going to fill up. And you have what? 2 minus 2 will give you 0 times 1 half will give you 0. What does this mean? He2 don't exist. That's the explanation that you can get from that. So this is the s orbital. Now, what if we have the p orbitals? How are we going to go on this? So it gives you the explanation why nitrogen has triple bond, oxygen has double bond, and fluorine has what we call the single bond. Okay? So what happened there? So this is already the S and the P. So the one that has the star there, that is your what? Anti-bonding molecular orbital. So it is molecular order 1 half the number of electrons in bonding minus the number of electrons in anti-bonding orbitals. Okay, so here with the exception, let's say, of the lithium, when you go here you can just cancel this out because they just has the same. And what you're going to do is just get the number from here, subtract it from the number here. So this is what? 2 minus 0, 1 half of that is 1. So this is 4 minus 0. Okay, 4, 1 half of 4 is 2. And this is what? 6, 1, 2, 3. So 6 minus 0 will give you 6 times 1 half will give you the triple bond of your nitrogen. And you have here 6 minus 2 will give you 4. 1 half of that will give you 2. And here you have 6 minus 4 equals to 2. And 1 half of that is equals to 1. Now what happened if you want to make this like O plus? So if that is a plus, that means you are removing an electron. If this is a minus, so that means you add an electron. So all you need is just, if you remove or add an electron, or if you have make it a positive or a negative charge, you just remove or add electron, okay, in the orbital that is of highest energy level. So those are the type of questions that can be asked to you. You can be asked, what is the bonding orbitals for, let's say, N2 plus? What's the bond order? So if it's an N2 plus, what will happen? You remove that one, right? So you have the 5 minus 0 equals to 5. And then you multiply by 1 half. So the bond order is 2.5. Ask yourself, can you answer questions like that? So you have to do some sort of a practice in doing this. I can ask you, what's the bond order? For let's say F2 minus. So I will have there 1 half. Okay. So if it's an F2 minus, so that means I'm going to add 1 electron there. So I have 6 minus 5. So I will have 1 half. Because just 1 times 1 half, or 0.5. So all the other system that we have here in this discussion is you just need to practice. Okay. And I'm hoping that you're doing this using your, what do you call that? Reviewer section, the chapter reviewer. Because that's the one that will definitely help you on this one. Okay. Now, You can also discuss there the magnetic character. So remember, how do we define diamagnetic and paramagnetic? So usually para is you have an unpaired electron. Dia is no unpaired electron. Or we could say all electrons are paired. So if you're going to look at this, so this is diamagnetic, there's no unpaired. This is paramagnetic, there's a unpaired. This is dia, all of them are paired. N2, this is also dia, and this one satisfactorily account why oxygen is paramagnetic because there's what we call the presence of lone paired. Okay, F2 is dia. Now, if I'm going to ask you what is N2 plus, is it dia or paramagnetic? So if you have an N2 plus, so that means you reduce that one, so that becomes from dia, it becomes paramagnetic because one of them has a lone pair. So that's the other information that you can get from this. Okay. Now, if you look at this, the localized molecular orbitals, they're not confined between the two adjacent bonding atoms. They can be extended over three or more atoms. Like for instance, the benzene. So they have the localized pi orbitals. Okay. So we could say you can apply this in resonance. Now, if we're going to look at the similarities between BBT and MOT, I think these are the summaries that you have there. The basic principle is the same in both theories. Both involve electron distribution. Whether it is atomic or molecular orbital, you cannot have more than 2 electrons. Now, both theories include the sharing of electrons by the nucleus or the nuclei. And according to both theories, the energy of overlapping orbital must be comparable and there must be similarities in their symmetries. Okay? Now, in terms of differences, this is, we could say, tabulated here. So, BBT, if we're going to look at this, the bonds are localized to two atoms, not molecules. In terms of MOT, the bonds are localized to two atoms as well as molecules. Okay? The valence orbital theory was first proposed by Hitler and Prince London. You're going to encounter London in Chem 112. And here, the molecular orbital was proposed by Mulliken and Fredrickson, the Hansrud thing. So BBT came first before MOT by 5 years. Okay, resonance plays an important role in this theory. MOT, there's no place of resonance in this theory. In BBT, it cannot explain the paramagnetic character of oxygen. In MOT, it satisfactorily explains the paramagnetic character. BBT is simpler in terms of calculation compared to MOT. So that's end the chapter that we have. Question? So as a reminder, you're going to have two experiments today. Experiment 10 and 11. So you expect to have two quizzes. So as I have told you, the quizzes that we have, you cannot take it late because it locks itself. Unlike the lab report, you can still submit lab report even if it's way beyond due date. Okay, so that's the difference that we have between the two. So you have your lab quizzes every Monday and Wednesday, and your chapter quizzes in the lecture, it's open between Thursday and Friday. And as I have told you, this is our what? If I'm not mistaken, after this, we just meet 2 more times for lecture. Okay? So we're almost over. So I hope you're doing your part. I mean, some of you are consistently doing your part. And I'm going to what we call I'm going to fulfill the rule that I have, that I'm going to open all the quizzes, at least the lecture. The lab, it's non-negotiable. Okay? The lecture, uh, if I'm not mistaken, I will open it next week, later part of next week when you take the chapter 6 quiz. All chapter quizzes are open and you are, okay? You can get at least 5 chapter quizzes of which you have a low score. So I'm willing to what we call look at the quizzes that you have that's low score. You can improve it by taking it one more time. Okay, in preparation for your final exam. So the final exam is a 2-hour exam, and you have to take it during class R. That's the last meeting that we have. Okay, so we already have two. We just have 2 more chapters after today. Chapter 5, which is the gases, and chapter 6, which is on heat. And by the way, you're not going to do experiment 9 in the lab. Okay, if you look at the syllabus, I erase it already there. Okay, and instead of that, you're just going to do the home experiment that I have already posted. So question,